This is a short lecture on conservation of angular momentum. So this is part 4 of Unit 6 in the AP Physics 1 curriculum. I suggest you get a pen and paper handy and take a few notes. Conservation occurs when there's no external torque acting on a rotating system. If you don't have any sort of a twist, then angular momentum will not change. So a consequence of this is that whatever initial angular momentum you have, that's what it's going to be when you look at it again later. Even if there's been things changing internally, if there are no external changes, angular momentum is a constant. It is a conserved property. Here's an example. Maybe you played this game before. This is tetherball. You whack the ball, it's tied to a rope, and it pivots around the pole. Now, if you're all by yourself, you're not actually playing the game, so there's one person here, and you strike the ball, you're going to give the ball angular momentum. It starts out a certain distance away from the pivot or from the pole, depending on which way you want to measure it. And as it rotates, the rope wraps around the pole, and that distance decreases. But all the angular momentum it has is what you initially gave it. If that angular momentum is constant, and if it depends on the radius times the linear momentum that you struck it with, then as the radius shortens, but the angular momentum stays constant, that means the linear momentum must be increasing. Now, linear momentum is a product of mass times velocity, and the mass stays the same. So that means the velocity must be increasing. So as the ball gets closer and closer to the pole, it moves faster and faster and faster as a consequence of the conservation of angular momentum. The slide basically just repeats what I just said. So here's an example problem. This is the same example problem that we used in an earlier lesson. And so I'm not going to work through it in detail, but basically you've got a ball swinging on a 0.28 meter string. The ball weighs 1.1 kilograms and it's moving at 3.2 meters per second. What is its angular momentum? Well, it's the radius times the mass times the linear speed. That equals 0.99 kilogram meters squared per second. Now, what would happen if we shorten that string? What would happen, for example, if you cut that string in half? Well, if you know the previous angular momentum, then you can use that now as a known value to figure out the new velocity. So the angular momentum was 0.99 kilogram meters squared per second. We're going to set that equal to RMV. In this case, we know R and we know M. We don't know V. So we're going to plug those values in, do a little rearranging, and find V equals 6.4 meters per second. So in case you forgot, when it was a radius of 0.28 meters, the speed was 3.2. Now the radius is cut in half and the speed has doubled. So that's a consequence of these three variables having to make up the same angular momentum as in the previous problem. If one of these changes, at least one of the others has to change in response. So I've been using this word, and I want to make sure you understand that when a property of any sort does not change before or after an event, we say that that property is conserved. I left off the TY there. Sorry about that. So angular momentum is a property in nature that is conserved in a system so long as you don't have an external torque or any other kind of input. So in sort of equation form, we could say that the initial angular momentum of a system is equal to the angular momentum at any other time. Let's call it our final time. And those two things are equal to each other. So this can be very useful because we have formulas for this. And what it's going to tell us is if one of the variables internally changes, then another internal variable must change in response, at least one other one. Now, in the previous example we were looking at with the tether ball, That's what we call a point object rotating around an axis. Let's look at an extended object which has the axis of rotation internally. Most famous example is a conservation of angular momentum when you have a figure skater. So if the figure skater has her arms or her legs extended, her axis of radius here is from the radius is very long. This is going to be a big moment of inertia. And so she's going to spin rather slow. But if she decreases her radius, that's going to decrease the moment of inertia. As a consequence, if the angular momentum is conserved, her angular velocity is going to greatly increase. And if you ever watch a skater do this, they can spin very, very, very fast. So again, for an extended object, the formula changes a little bit. We look at moment of inertia and angular velocity. And like I said, if the moment of inertia decreases, then this angular velocity must increase if L remains the same number. For example, if L was 100 and I was 10 and omega is 10, but now I decrease I to 5 and L stays 100, omega has to go up to 20. Whatever factor I goes down, omega must go up by the same factor. Here's a sort of a typical AP example problem. They love to have disks that are rotating. So this one has an angular velocity of 9.2 radians per second, and it gives us the moment of inertia, 13 kilogram meters squared. What would happen to the angular velocity if an identical disk that was not originally rotating is dropped on top of the original disk? So we've got a disk that's spinning and another one sort of plopped right on top, like two pancakes. All right. The second disk is not spinning. All right. So the original disk has an angular momentum of moment of inertia times omega, 13 times 9.2, gives us about 120 kilogram meters squared per second. So our original angular momentum is around 120, and assuming it is conserved, and assuming that the second disk has no angular momentum, then the combination of the two disks is going to still keep 120, the original angular momentum of the first disk. But now, since they're identical, we're going to have twice the moment of inertia times the same angular velocity, the same moment of inertia times 2, but our angular velocity has to change. And so it's going to go down to 4.6, which is half of 9.2. It's half the mass doubled, the speed was cut in half. So when the second disk landed on the first in that example, and it starts rotating, both the disks have angular momentum. And one of the things that we just assumed that was left over from an earlier video is that whenever you have two objects and they both have angular momentum, then the total, you just add them together. But in this case, our original angular momentum was 0. We still have to take that into account. So we had 120 with the momentum units plus 0. And now that's got to equal the angular momentum of both disks when they're stacked together. Since they're identical disks, you just cut it in half. So each one of these will now be 60 kilogram meters squared per second angular momentums. Now that's sort of an extreme example where you have two things that are exactly the same. In real life, you can have two things that are completely different strike each other. And they can both be rotating, and they can be rotating in different directions. A good example of this is I love to play pickleball. And in pickleball, sometimes the ball is spinning when it gets to your paddle. And if you swipe your paddle across it, you can apply the same spin or an opposite spin or maybe a perpendicular spin to it. And the ball can fly off at different angles depending on how experienced you are, how good you are at hitting it. Anyway, for example, imagine that you have a disc that's spinning with some initial angular momentum, L, and now a clay ball is thrown at the disc and sticks to it, causing the disc to speed up. If you look at both objects, the disc and the clay ball, as part of the same system, then the angular momentum must be conserved. but the ball was not originally spinning. It was traveling linearly. So how can it change the angular velocity of the disk? If angular momentum is conserved, and we got this disk that has some angular momentum, and we get a ball that apparently does not have angular momentum, how did we change that? Why did the disk speed up? Well, there's probably three ways that you can look at this situation. First, you can realize that the clay ball was moving, and so it had linear momentum. So although we give linear momentum and angular momentum a different name and a different equation, they're actually the same thing from a universal standpoint. They're inertia in motion, okay? So in that sense, the clay ball's linear momentum is simply changed into angular momentum. It's a second way of looking at it, very similar to that, is if you think about kinetic energy versus potential energy, they can change into each other. Well, it's sort of the same way with momentum. If you look at it as the clay ball is moving and has the potential to change angular momentum if it strikes something at an angle, then that's one way to look at it. The straight path of the clay ball becomes altered, and then it's constrained then to spin about an axis itself. So it was going straight, and all of a sudden it's forced to spin, but it didn't lose momentum. It just changed it from linear into angular. The other way to look at it is that here's the clay ball, here's the spinning disc. I'm going to stick it to this outer edge right here and make this disc spin faster. So this doesn't have to be initially spinning, but it's going to spin after it sticks. And so that's going to affect the velocity of this disc clay ball system. So that's the key. Is you look at both of these as part of the same system. Then you could say, here's my axis of rotation. Even though this isn't attached here yet, it does have a distance from that axis of rotation. There's a distance when the ball is there. When the ball gets closer, there's a distance there. When the ball sticks here, there's a distance there. So you could say that it actually does have angular momentum with respect to this point. As long as this thing is moving, it has some kind of angular momentum with respect to a pivoting point. And so that what's changing is the disk has the same R as it spins around, but the ball's R is constantly changing until it sticks, and then it becomes a constant too. But as this changes and mass stays the same, this has to compensate. And so what actually happens is the angle is changing. So this formula, RMV, this assumes that the velocity is tangential. In other words, it's striking perpendicularly. But the ball's not perpendicular necessarily until it sticks. So we actually have to use the sine of the angle that it makes. Anyway, here's an example problem just like that. So here we have a disk with radius 1 meter. We're given the rotational inertia, thank goodness. That's 0.5 kilogram meter squared. So the disk is free to rotate, but it's initially at rest. I always make a note of that. You should probably circle that every time you see that word. A blob putty with a mass of 0.1 kilograms is traveling toward the disk with a speed of 10 meters per second, as shown in this figure. The putty collides with the outermost portion of the disk and sticks to it. What is the angular momentum of the combined disk-putty system after the collision? Well, if both of these are part of the same system, then whatever momentum they had before, that's what momentum they have afterwards. And so you could figure out the individual momentum and add them together. Now this is at rest, so it initially has no angular momentum. So I'm going to call that L1 naught. This is in motion, and so I'm going to call it L2. The angular momentum of the putty, I'm going to designate with a 2, is when it sticks out here, 1 meter away times 0.1 kilogram mass times 10 meters per second. So that gives 1 kilogram meter squared per second for the angular momentum. Now, like I said, if this property is conserved, then we add those two things together. The total momentum just right before the putty sticks is 1 kilogram meter squared per second. just add these two values together. Well, that's also the momentum afterwards. So in other words, the initial momentum added together equals the final momentum. Now they're stuck together. I put 1 plus 2 in the same momentum here. Well, if this equals 1, this must equal 1. And so the answer to this question is B. Now, I want to emphasize again that in this case, we looked at the clay and the putty as being part of the same system. When you're reading your AP problems, you got to make sure that's what they're talking about. A lot of times it's implied and not explicit. But if they're part of different systems, that will be explicit. They will say that out loud. So if they don't say they're different systems, assume they're part of the same system. And that's super important because any changes inside a system doesn't affect the angular momentum. If you assume that the putty or the clay ball in the example before was part of a different system, then the angular momentum of the disk would change. Systems can gain or lose momentum, whether it's angular or linear. They just have to get it from another object or system. So conservation of angular momentum applies when there's no external torque or input to the system of interest. But if you, even if you didn't look at it that way, if you think about momentum as being some property the universe has, the total momentum in the universe, angular or linear, remains constant. So when one system picks up momentum, another system must lose it. If one system loses it, another one must pick it up. The total momentum in the universe remains the same. Okay, momentum is not created or destroyed. That's what the ultimate point of conservation principles means. So here's your takeaways. Angular momentum is conserved if there is no external torque applied to your system, whether that system is a point object, whether it's an extended object, or whether it's a collection of objects. As long as you have no external torque, then the angular momentum is conserved. The angular momentum you have at the beginning of a problem is the same total angular momentum that you have at the end. Individual objects within your system can change. They can change their torques, they can change their angular velocities or whatever, but the total must remain constant as long as there is no external torque applied. And even objects moving in a straight line can be said to have angular momentum with respect to some point that you pick as the axis. All right, we just used the L equals MRV formula, or maybe you have to multiply by the sine of theta. But the point is that even as, like the clay ball or the putty, you can think of those as having angular momentum within your system, even though they aren't stuck to anything yet. That's the end of this unit. You should go and look for a set of problems to do now.